The next type of transformations we're going to look at in this section are stretching and shrinking. We have seen that by adding or subtracting a number, whether it be in the inside or outside of a function, creates a shifting effect, whether it be horizontal or vertical. The next type of operation we're going to see is what happens when we multiply either on the inside or outside of a function, and we're going to see that the effect this will have will be of a stretching or a shrinking effect. For example, let's start with the graph of f of x equals x squared, which is one of our parent functions. We know that its graph looks like a parabola. It's the curve listed here in this graph in black. And along with that graph, we're going to look at the function g of x, which is 2x squared. That function is simply going to be twice our original function f. So the way that g is related to f is it's twice f. And if we look at the graph of g of x, which is the graph that's in blue, what we would notice is that it's going to be kind of a stretching effect where it rises more sharply than what the graph in black does. To be more precise, if we kind of zoom in a little bit, if I pick any point on the graph of f of x, okay, for argument's sake, let's look at the point at 2, 4, which should be represented by this point here in black. So that's this point right here. If we wanted to look at the corresponding point on the graph of g for the same x value, remember that g of x is twice f of x. So what you would see is that the similar point that's going to be on the graph of g for the same x value is going to have a height that's twice as much. If we take 2 times 4 and we double that, that would give us the point 8. And overall, you can kind of see that essentially comparing for any x value, the point on the blue curve will have exactly twice the height of the point on the black curve. And so we would say that that's going to be a vertical stretch by a factor of 2. We can also look at the graph of h of x, which is equal to 1/2 x squared. The way that h relates to our parent function f is that h of x is half of f of x. If we look at the graph, h of x's graph is depicted in red or maroon. What we see here is that if you look at any point on the graph of f of x, let's suppose we look at the point 2, 4, the graph of h of x, which is 1/2 of f, is going to have a height which is half as much. So when x equals to 2, we see that the graph of f of x is at the height of 4, whereas the graph of h of x will be at half the height, which is a height of 2. Again, kind of comparing these, so what do we see? If you're looking at the comparison between the curve in red versus the curve in black, we would say that h of x is obtained from the parent function f of x by vertically shrinking each point by a factor of a half. So to summarize, this is what happens when you multiply on the outside of a function by a number. So if the multiplication is taking place on the outside, and let's just assume for a moment that c is a positive value. If c was negative, then what you would have would be a combination of transformations, which would be a stretch and a shrink, along with some type of reflection that we saw previously. So let's just for a moment focus on the stretching and shrinking behavior. So let's suppose we're multiplying the function f of x by a number c. If c is greater than 1, then essentially we're multiplying these heights by values bigger than 1, which will create a larger y-coordinate compared to the original graph of f. And the effect that that's going to have is that it's going to vertically stretch the graph by a factor of c. So it's going to be a vertical stretch by a factor of c when c is greater than 1. So if we look at this graph here, if our parent function is in blue, if we multiply that by c, you can kind of see that it's vertically stretched in the y direction. A good kind of intuitive way to kind of think about this is that the function and its stretch will have the same zeros. At the end of the day, if you multiply any function by 0 by a number, you're still going to get 0. So they'll still share the common zeros. And if you kind of think of those zeros almost as like thumbtacks, And think of the function almost as if it was like made out of a rubber band. Essentially, what you're doing is you're pulling away from the x-axis. Okay, so you're kind of stretching the graph away from the x. So up when it's positive, and down over here where it's negative. Conversely, if we multiply by a value c that happens to be between 0 and 1, so like a fractional value like a half or 0.3, etc., then the effect that has is that's going to vertically shrink the graph of f. So it's going to kind of compress it and move it closer to the x-axis. Let's take a look at example 9. We want to use the graph of f of x equals the absolute value of x to obtain the graph of 1/3 the absolute value of x. So first things first, let's start off with our parent graph. We know what the absolute value graph looks like. It's piecewise linear. And for this first one, let's make a table of values here. Here's x. Here's f of x, which is the absolute value of x. And I'll keep track of just kind of like these 3 key points. We have -1, 0, and +1. Right. The absolute value of them all is going to be equal to 1. And now let's look at the graph for the function g of x. And I'll do this in a slightly different color. And I'm going to graph the same 3 points. So g of x is 1/3 the absolute value of x, which is simply 1/3 f of x. So we have -1, 0, and 1. And the corresponding values for g, are exactly going to be 1/3 those of the corresponding values for f. So for g at -1, it's going to be 1/3 of f's value. 1/3 of 1 is just 1/3. 1/3 of 0 is 0. And 1/3 of 1 is going to be 1/3. Let's go ahead and graph those points. So we have 0, 0, which is right here. We have 1, 1/3, which would be right here. We have -1, 1/3, which is right there. And now we can kind of go ahead and draw the shape. Okay. And so this would be the graph of 1/3 the absolute value of x. And again, you can see what the effect is going to be here by multiplying on the outside of the function, the parent function, by a number between 0 and 1. The effect that this has created is it's a vertical shrink. So it's a vertical shrink and it's going to be by a factor of a half. It's going to be by a factor of a third. Let's take a look at another example. In the next one, we want to use the graph of the cube root of x to obtain the graph of g of x, which is 2 cube roots of x. The way that g of x relates to f is that g of x is going to be twice f of x. So let's go ahead and graph, first of all, our parent function, which is going to be the cube root. And let's label a couple important points here. So we should all know what the parent function for this looks like. Should look like this. And let me just kind of highlight a couple key points that are on the graph of f here. The cube root of -8 is -2. The cube root of 0 is 0. And then the cube root of 8 would be 2. To graph the function g of x, which is going to be 2 times f of x, all we need to notice is that for every point in g, it's going to have a height, which is going to be exactly twice that of the y value for f. So for example, if -8, -2 is on the graph of f, then the point -8 comma twice -2, which is -8, -4, is going to be on the graph of g. That would be right here. If 0, 0 is on the graph of f, then the point 0, comma 2 times 0, which is simply 0, 0, will also be on the graph of g. And if 8, 2 is on f, then the point 8, comma 2 times 2, which is 8, comma 4, would be on the graph for g. And then once we kind of know what the overall shape is, just go ahead and nice and neatly connect your dots. So this would give us the graph of g of x, which is equal to 2 cube roots of x. It was obtained by knowing the parent graph of f of x, which is the cube root, and we have a vertical stretch by a factor of 2. So this is a vertical stretch by a factor of 2. Another kind of transformation we're going to look at is what happens when we multiply on the inside of a function by a value. Once again, let's just assume for the moment that c is going to be positive. If c is a negative value multiplying on the inside, then that once again becomes a combination of two transformations. It would be the combination of a reflection along with a horizontal stretch or shrink. So for right now, let's just focus on the horizontal aspect of it, the stretching or shrinking part. Much like what we kind of saw when we were looking at horizontal translations, how, it's a little bit maybe counterintuitive that when you add on the inside, it actually moves it to the left, and how you subtract on the inside moves it to the right. The stretching and shrinking part is something also kind of too that might be a little bit counterintuitive at first. If we multiply on the inside of a function, so f of c times x, so the multiplication by this constant c is taking place on the inside. If c happens to be greater than 1, then this actually is going to create a horizontal shrink. Conversely, if we're multiplying on the inside by a value, let's say 0 less than c less than 1, then this is actually going to be a horizontal stretch. To see why this is the case, let's just start with maybe the graph of a square root of x. So let's think about this value, this for a minute. Let's suppose I have the function y equals f of x, which is the square root of x. And let's focus for a minute on getting the output of 0. Obviously, if we put 1 into the function, that's going to give us the output of 1. So here's 1, here's an output of 1, and this corresponds to the square root of x. If we look at a transformation of this, let's look at the transformation g of x, which is equal to the square root of 4x. And let's suppose that we also want to get an output of 1 for this. In order to get an output of 1, we would need for 4x to be equal to 1. We can solve this. We can square both sides. That would give us 4x equals to 1. And divide both sides by 4. We would get x equals 1/4. So that same value that happens when x is equal to 1 for f would occur at 1/4 for g to get the same output. Another way to think of this is, because of the additional factor of 4 here, that's a factor that's greater than 1, for every x value we plug in, it's going to be 4 times as much as the comparable value we would be plugging in to f under the square root. So in essence, to get a similar kind of output, the x value that you would be plugging in would need to be 1/4 as much. And if you're using an x value that's 1/4 as much, that's going to be further back along the x-axis, closer to the origin. And what we can kind of see is it's going to take that graph, and that's going to create the shrinking effect. Right? So we're multiplying by a number bigger than 1 on the inside, and that's going to shrink it. Or if you want to look at what would happen with something like this, perhaps, if we have, let's say, h of x is equal to the square root of 1/10 times x. If we think about what would we need to plug in here in order to get an output of 1, well, we know that we would need to have a 1 on the inside. So the value for x there would need to be 10. So for this function, it would have the value of 1 way over here at 10. So it's been moved and stretched to the right. That's a horizontal stretch when the constant value inside is between 0 and 1. Okay? So the moral of the story is, again, multiplying on the inside of a function by a value is going to be a horizontal stretch or a horizontal shrink. Numbers greater than 1 shrink the graph horizontally. Values between 0 and 1 would actually take the graph and stretch it horizontally. Same kind of analogy if you want to think of it like I gave the rubber band analogy a little bit ago. But if you look at the parent function, being the one that's kind of in maroon here in each graph, the zeros don't change. If you multiply 0 by any number, it still stays as 0. So think of the zeros, excuse me, not the zeros in this case. The zeros will actually move. But just think of that about each point here. Wherever point you have on the graph, it's going to be scaled and moved kind of like in that direction. So you can definitely think of it as being kind of tacked in on the y-axis. So the y-intercept this time, the y-axis, that would be like a kind of like a thumbtack where everything is kind of fixed on the y-axis. And then what we're doing is we're kind of simply taking that rubber band, but you'd be kind of pulling it along the x-axis. So pulling it along the direction of the x-axis, or conversely, if it's shrinking, you're taking that graph, you're kind of pushing it like an accordion. You'd be pushing it in and contracting it and make it look closer to the y-axis. Let's look at an example of this. In example 11, they give us some kind of parent graph, which is this graph here. And we want to find the graph of f, which is 2x, and the graph of f, which is going to be 1/2 x. In order to do this, let's kind of write down a table of values here. So for the original graph of f, some of the key points we see that happen here, we have -4, 0, which is this point. We have -2, 4. We have 0, 0. We have 2, -2. And then we have 4, 0. If we wanted to think about what's going to happen for the corresponding values for the graph of f of 2x, we're multiplying on the inside, and this is going to be by a value that is bigger than 1. So c is equal to 2, which is bigger than 1. So this should be a horizontal shrink. Let's see if we can figure out in our table, let's figure out the same corresponding values for f of 2x here. We know the output 0, 4, 0, -2, so those don't change. Because it's a horizontal shrink, it's going to affect our x values. For example, when we plug x equals -4 into the original, we get the output of 0. So to get 0 out of f of 2x, we need the input, which this time is 2x, to be equal to that original x value of -4. -4 divided by 2 will give us -2. And what we kind of do, if you kind of compare these two, how are these changing? Well, the answer is we're simply kind of taking the original x value, which was -4, 0, and we're multiplying it by 1 over c times x. And then that's going to be the point that'll be on the graph of f of cx. So to get the corresponding x values for this one, all I'm going to do is take each of those x coordinates, and I'm going to multiply it by 1/2. 1/2 of -4 gives us -2. 1/2 of -2 gives us -1. 1/2 of 0 is still 0. 1/2 of 2 is 1. And 1/2 of 4 is 2. Let's now go ahead and plot these ordered pairs for the graph of f of 2x. The first ordered pair is -2, 0. The next one is negative 1 comma 4. We have 0 comma 0, 1 comma negative 2, and then we're going to have 2 comma 0. We know the overall shape of this thing, so we can now go ahead and graph it. It's going to look like this. And what you see is that the graph that's in green, that would represent the graph of f of 2x. It's obtained by taking the original parent function's graph of f, but we're vertically shrinking it by a factor of 2. So for each point we had on the original graph of x, comma f of x, we're going to have the corresponding point which is going to occur at 1 over c times x, f of cx on its graph. Let's now do the same thing. Let's take a look at the graph of f of 1/2 x. And I'm just going to kind of use a little utility here. Let me just use the same graph again, and I'll superimpose that graph over top. So again, this is going to be a horizontal stretch this time, because we are multiplying on the inside by a value c, which is between 0 and 1. If it helps, we can again make a table for this one. Here we have the new x value. We want to find the graph of f of cx, which for this one is going to be 1/2 x. We know the outputs 0, 4, 0, negative 2, and 0. And now we want to figure out where do these corresponding values for f of 1/2 x occur at that came from f of x. Again, it's going to be 1 over c times your x value, the original x value. This is going to be 1 divided by, notice in this case, c is a half. And 1 divided by half is 2. So what we need to do is take 2 times the original x value that was over here. For the first one, we're going to get 2 times negative 4. That's going to be negative 8. 2 times negative 2 is negative 4. 2 times 0 is 0. 2 times 2 is 4. And 2 times 4 is going to be 8. We now have our points. Let's go ahead and plot those. We have negative 8, 0, which unfortunately does not fit on this graph. But that would be like way, way over here. We have negative 4, 4 would be here. 0, 0 is still there. We're going to have 4, negative 2. And once again, we ran out of room. We would have 8, comma 0 should be over here. We know the shape, so we can kind of go ahead and fill it in. And that would be your graph. The graph that's in green would be f of 1/2 x. It's simply going to be the graph, the parent graph f of x, but with a vertical stretch by a factor of 1/2. Okay. Technically, the factor, by the way, so when you see that 1 over c times x, the factor itself is 1 over c. So this is going to be 1 over a half, which would be 2. So it's a vertical stretch, and technically the factor is 2. You can see that every x value on the graph of the new function is located at an x coordinate that's exactly at twice the corresponding point for the function f of x. The last thing that's in this section is combining multiple transformations. A lot of times we'll be asked to graph functions that have a combination of these simpler ones. When this kind of appears, it's important to kind of follow an order to do these. For example, if you notice that a function is a transformation of a parent function, you want to kind of graph it by using these transformations to the original. You would want to begin by doing any horizontal shifting. Then we would follow that up with any stretching or shrinking, both vertically and horizontally. The next step would be to handle any reflections that you might have. And then lastly, to handle the vertical shifting. So horizontal shifts, stretching and shrink, reflections, and then lastly is the vertical shift. Let's take a look at an example of this. In example 12, we are asked to use the parent function f of x below to obtain the graph of negative 1/2 f of x minus 1 plus 3. So first things first, we look at, there's obviously quite a bit that's being done here. The fact that we have a subtraction by 1 on the inside means that we will have a horizontal shift. And that's going to be 1 unit to the right. We also have on the outside a multiplication by 1/2 on the outside. That's going to be a vertical shrink. By a factor of 1/2. The fact that it's a negative 1/2 on the outside, that negative symbol there itself means that we are going to have a reflection. Remember, on the outside, the negative multiples mean a reflection with respect to the y-axis. So we have a y-axis reflection. And then lastly, because we have a plus 3 on the outside that's adding, that's going to be a vertical shift up 3 units. So in order to handle this, you can try to move each point individually according to the scheme, or a lot of times what I like to do is to kind of do it in steps. So do each of kind of like the basic and baby transformations first, and then put it all together at the end. First thing, let's handle the horizontal shift. We need to take each one of these points and shift it 1 unit to the right. What that's going to do is if we have these ordered pairs, that's simply going to take each x coordinate and add 1 to it. So the point that was at negative 4 comma 0 is now going to appear at negative 3 comma 0. This point that was at negative 2 4 now appears at negative 1 4. The point at 0 0 will now appear at 1 comma 0. 2 comma negative 2 will now appear at 3 negative 2. And the point that was at 4 0 now gets moved 1 to the right and now appears at 5 0. So we can now go ahead, let's graph that portion of it. It's going to look like this. And that part would represent the graph of f of x minus 1. So that handles the horizontal translation part. The next thing we're going to work with is the vertical shrink by a factor of 1/2. To vertically shrink this graph by a factor of 1/2, what that means we need to do is for every y value of every point we have here, it's going to have half the y value for the transformation. For example, if we look at this ordered pair here, this ordered pair is at negative 4 comma 0. If we take half of 0, that's still going to be 0. Excuse me, that should have been negative 3. So that point's not going to move. That's still going to be at negative 3 0. If we look at this point right here, however, that point was at negative, if I get my points right today. Yeah, there we go. That point is at -1, 4. When we take half of its y-coordinate, half of 4 is going to give us 2. So that's now going to be -1, 2. The point at 1, 0, half of 0 is still 0, so that point stays the same. For the next point, the point at 3, -2 is now going to get moved to 3, -1. And the point that was at 5, 0 will still stay at 5, 0 because half of 0 is still 0. You can go ahead, graph this. This now accounts for the factor of 1/2. So right now, this would represent the graph of 1/2 of f of x minus 1. The next transformation we have is a y-axis reflection because we are multiplying on the outside of the function by a negative. When you multiply on the outside of a function by a negative, that's going to reflect this about the excuse me, did I say y-axis reflection? Oh, sorry. That's x-axis reflection. My apologies. Inside, multiplying by an inside is a y-axis reflection. Multiplication on the outside is going to reflect it about the x-axis. Essentially, what's going to happen here, so any point that's on the x-axis is still going to stay in the same spot. So your -3, 0, 1, 0, and 5, 0, those points stay the same. -3, 0, 1, 0, and 5, 0, those all are still going to be there. What's going to happen now, for example, if I look at this point here, which was located at -1, 2. If I'm multiplying on the outside, in other words, if I'm multiplying that y value by a negative, then that point is now going to get moved to -1, -2. So instead of being above the x-axis, it's going to get reflected down below and end up here. So we're going to have the point -1, -2. And similarly, the point over here, which was at 3, -1, that y value gets reflected across, and so that's now going to be at 3, +1. Like this. And then go ahead and kind of put in the shape. This would now represent the graph of -1/2 f of x minus 1. And then the very last thing we need to do is we also have a vertical shift by a factor of 3. So we now want to take and add 3 to each of the y components. So the point here, which was at -3, 0, is now going to be at -3, 3. The point at -1, -2 is now going to be at -1, +1. The point at 1, 0 is now going to be at 1, 3. The point at 3, 1 is now going to be at 3, 4. And the point that was at 5, 0 is now going to go to 5, 3. Once again, we know the shape. Fill in the shape. And now this represents the graph of -1/2 f of x minus 1 plus 3. And that graph right there is your final answer. And the way that we were able to get it is by kind of doing a series of transformations. So break it down, do step by step. Again, for that list of transformations, this is the order you want to follow. Horizontal shifting. Any stretching or shrinking, the order of those doesn't matter. You can do horizontal or vertical first. Once you've done those, you would then want to look at either any y-axis or x-axis reflections. And then always lastly, you want to look at the vertical shifting. Okay. And so when you compare our final answer, which is this graph, we can see how in many ways it has kind of the overall shape of the parent function, but with all of those different changes. I'll let you try 13 and the rest on your own, but the next section we're going to look at is combinations of functions, which for us is going to be a very important section in this class.